I'm super excited about the lecture today. So before the course, I was kind of figuring out how the lecture materials were going to look and preparing slides. And some of the slides in this lecture is actually what I started with because I was just so excited to talk about these topics. I think that they're like extremely mathematically satisfying and kind of visually satisfying. So hopefully you enjoy it as well. The other thing I want to say before we jump in is I think these topics, when I was kind of first learning them, it took me kind of a few times through before it really clicked in my mind. Maybe that's just because, you know, they weren't presented as beautifully as I'm about to present them to you now. So maybe that won't be an issue for you. But I think some of these you kind of just have to sit with them for a little bit. So maybe watch this lecture, go back to the textbook, maybe watch this lecture again. It just might take a few times before they really click. Okay, but with that, let's jump in. So over the last week and a half or so, we've been talking about the task of falsification, where we're just trying to find failures of a system, maybe the most likely failure, maybe any failure we can find. But so, you know, sometimes maybe we want more than just like one most likely failure. We want to know like what is the full distribution over possible failures that we might observe. So today we're going to talk about how we can kind of take that one step further and try to sample from the full distribution. And as you'll probably see, the process for doing that is maybe like a little bit more complicated, a little bit more difficult, but you get kind of this extra reward of now having like the full distribution over failures that you might see. Okay, so let's talk about like mathematically what is actually the failure distribution. So in previous lectures, we've talked about this thing that we're calling the trajectory distribution, which given a trajectory tells us how likely that trajectory is. And so this is basically kind of, you know, the distribution over all possible trajectories we might observe. And then we're just going to extend this to the failure distribution by creating a conditional probability. So we're going to say that the failure distribution is this probability conditioned on the fact that tau is a failure, that our trajectory is a failure. So if you remember this kind of tau not in psi notation, just means that tau is a failure. Okay. And it turns out that we can actually write this distribution out like this. We can expand it out. So let's just focus on the numerator really quick. So what's going on here is this kind of 1 with the curly brackets. That's the notation that we use in this course for the indicator function. So all this function is doing is saying if tau not in psi, so if tau is a failure, this function returns the value of 1. If it is a success, it's not a failure, then this function will return a value of 0. And then this p of tau here is just our nominal trajectory distribution. So what this numerator is basically it will return p of tau if our trajectory is a failure, because this will evaluate to 1. And if our trajectory is not a failure, this numerator will be 0. And this is really just kind of what's going on to get the failure distribution. But there's one extra thing we need to add in, which is this denominator here, because this will not integrate to 1. Because now we're assigning some trajectories in our full trajectory distribution to a probability of 0, so it's not going to integrate to 1 anymore. And so we actually need to divide by this integral in order to create a valid probability distribution. So we're going to integrate this over all possible trajectories to get the failure distribution. Okay, so let's kind of visually see what all of this looks like. And we're going to use a very simple example. And so those of you who have started Project 1 will recognize this. This is actually the example that we use for the small system in Project 1. It's a super simple system where trajectories basically just consist of one state. So we just sample an initial state, and that's it for the trajectory. And this initial state, so our tau is just this state, is sampled from a Gaussian distribution that looks like this. So our nominal trajectory distribution is just this white distribution here that we call p of tau. And now let's kind of look at what the components of this equation look like with respect to this distribution. So we're going to say that our trajectory is a failure if that state that we sample is less than some value. So for example, -1 in this case. So anything to the left here is a failure. Anything to the right here is not a failure. And now let's look at just what this numerator part here, looks like with respect to this particular system. So this numerator, again, we said it just evaluates to the nominal trajectory distribution when the trajectory is a failure, and then it evaluates to 0 otherwise. So that's exactly what's happening here. This red line shows that numerator, where we're getting, the same exact value as the nominal trajectory distribution for the trajectories that were a failure, the ones that were less than -1, and then we're getting a value of 0 for all other trajectories. Okay, and then for the denominator, this is kind of the integral over all possible trajectories of this value. So we know from calculus that that integral is just going to be the area under this curve. And this is just a constant value. So the way that we can kind of think of this is we take, this distribution here, and we divide it by this constant value. That area is not going to change based on tau. That area is always the same because we're computing it over all possible tau. And so all it's really going to do is scale kind of this value so that the area under the curve now is equal to 1. So this is now a valid probability distribution. So what I'm trying to say here is basically this numerator here is really what gives us the actual shape of the failure distribution. So we had, this shape here, and then this denominator is just what we compute to scale that shape such that we get a distribution that will integrate to 1. I'll pause for questions on that. Any questions? Oh, yeah.
So is each trajectory like a dot when you have a curve?
Yeah, so the question is is each trajectory like a dot? Yeah, so if you've done the project already, you'll remember every single trajectory is just one sample from this distribution, so just one dot, yeah. And then basically this distribution tells you okay, if I got this trajectory, what is the probability of that trajectory under the failure distribution? Okay. So yeah, the top one gives us the shape, and the bottom one gives us kind of this scaling factor that we call the normalizing constant. But it's just a constant, it just gives us that area under the curve. Okay, so this is our failure distribution, and if we could compute this, then we would know the failure distribution for all of our systems. But kind of the main problem here is that typically this denominator, this integral part here, is very difficult to compute. Sometimes it's even impossible to compute. So we're kind of bummed we can't actually often compute an analytical expression for this failure distribution. But one thing that is nice is we can compute this numerator. So you might remember kind of a similar theme we had earlier in the class when we were talking about Bayesian estimation, where we had a similar idea. We can, given a particular trajectory, we know how to compute the numerator of this equation. Because to compute this first term here, we just need to check whether or not that trajectory is a failure. And if it is a failure, we return 1, and if it's not, we return 0. And to compute this term, we just need to evaluate the likelihood of that trajectory under the nominal trajectory distribution. And we talked in the previous chapter, when we were talking about likelihood objectives and things like that, we already talked about how to compute the probability of a particular trajectory occurring. So we can compute this numerator is kind of the key idea here. And if you remember from the previous slide I was just showing, the numerator is really what gives us that shape of the distribution. So it turns out just knowing this numerator is enough to kind of do interesting things, as we'll see. And what we call this typically is an unnormalized probability density. So it gives us the right shape for our probability density, it just doesn't integrate to 1. So it's not a valid probability distribution, but it can still tell us things. So in this class, when we talk about unnormalized probability densities, we're often going to talk about or denote them with kind of this bar over the variable. So this is just showing us the unnormalized failure probability density. And it's equal to that numerator there. And what's really cool about this is that there are algorithms that actually allow us to draw samples from an unnormalized probability density. So we already talked about this a little bit previously when we were talking about the Bayesian estimation, and I was like, there's this magic that happens, and you can take this unnormalized probability density, and you can get all of these samples. So we're going to talk a little bit today about what that actual magic really is. And this way, we can't actually maybe explicitly write down the failure distribution, but what we can do then is implicitly represent it by just drawing a bunch of samples from that distribution. So for example, in the grid world, we can sample from its failure distribution, get a bunch of different trajectories that are part of that distribution, and just plot them all together. And this kind of gives us an idea of what the distribution over failures for the grid world system looks like. Yeah, do you still have your question? Or? Yeah.
So I guess maybe I'm just not understanding the
curly braces?
Yeah, but yeah, I guess is this saying the likelihood that a failure happens within the full probability of trajectories? Is that kind of it's the same, or maybe I'm just
It's like you got a trajectory and you want to know what is its likelihood under the distribution over failure. So let's say maybe you found a failure trajectory and you're like, compared to the whole distribution over failures that could possibly happen, what is the likelihood that I got this failure? That's kind of what it's supposed to be describing. This side? Yeah, well, so these are equivalent. So this is just another way of writing it that's easier for us to work with. So what this distribution is saying is what I was just describing. And it turns out we can write that in an unnormalized way as the nominal probability of that trajectory occurring times this indicator that just gives it, will return 1 if it is a failure and 0 otherwise. Because if we observe a trajectory and that's not a failure and we're like, what is the likelihood under the failure distribution? Well, that's 0 because we're trying to sample failures, so there just is no likelihood. Yep. What other questions do you have on this? Yeah.
So this doesn't take into account robustness, right? And the idea that a failure is a failure and there's a hard cutoff between not failure and failure.
Yeah, so the question was, this doesn't take into account robustness. You've alluded to something that's going to happen at the very end of lecture. That we'll take care of that. Anything else? Yeah.
So why is it hard to calculate that denominator, like the normalizing constant? Is it just because it's really hard to know all the different ways it can fail?
Yeah, that's pretty much exactly right. And it turns out, so the denominator, it's an integral over all possible trajectories. So we need to now take into account every single possible trajectory to compute that integral, which is generally not easy to do. And in fact, we're going to find out next week that's actually equivalent, computing that integral is equivalent to computing the probability of failure, which is difficult to do. And we're going to talk about a whole bunch of methods for actually doing that estimate next week. All right, so that's kind of setting up the problem. And now today we're going to talk about different ways to actually go about drawing samples from a density that we don't have the normalization constant for. So one of these techniques is called rejection sampling. Another technique is called Markov chain Monte Carlo. And then the final thing I'll talk about is just like, throughout this lecture, I'm going to mostly just show this kind of like 1D Gaussian system. It's kind of silly. We already know a lot of things about Gaussian distributions. We could just like analytically compute the failure distribution for this one if we want to. So this is all just kind of a way to get you some intuition, but these things really do scale up to things that are more than just this one-dimensional Gaussian, and we can actually scale them up to, like, for example, the pendulum system, which has 50 dimensions, 100 dimensions, and it's pretty cool to see the way that these things scale up. So towards the end, we'll talk about how to actually like move from our 1D Gaussian to these bigger systems. But okay, let's dive into rejection sampling. And we're gonna think about rejection sampling by first using this analogy of a dartboard. So let's imagine that we have this kind of rectangular dartboard here. So it might not look like the dartboards you're used to, but it's basically a big rectangle that we can throw darts at and they'll stick on the board. And the first thing that we're gonna do is draw the shape of the target unnormalized density that we want to sample from on this dartboard. So this is just the shape of the density, which you remember we can compute with just that numerator there. And we're just going to draw it on the dartboard. And then what we're going to do is we're just going to throw darts uniformly at this board. So we're just going to like assume that somehow we can actually just kind of uniformly throw a dart and it'll end up in some random spot on that board. Then the next thing that we do is we look at all the darts that we just threw, and we separate the ones that landed above this target density that we drew on the board from the ones that landed below this density. And then here comes the rejection part. We're going to reject all of the darts that landed above the target density. And then it turns out if we just kind of take the value on this axis for all of those samples, so basically we drop all of those samples kind of straight down to the bottom of the dartboard, then it turns out now these samples are actually distributed according to this density. Kind of insane. And
can you do that one more time?
There'll be more.
Okay.
Yeah, it'll play a few more times. Okay. The next part's even better. So this is kind of hard to see that these are really distributed according to this distribution. But one thing that we could do to kind of convince ourselves of this is you could imagine just kind of binning up this axis here, and then taking all of the samples that landed in each bin and stacking them on top of each other. And so if we do that, then you can see why I started with these slides. And so if we do that, you see that they actually look like they're kind of distributed according to this target density. And then another thing you can imagine is like the more darts we throw, the more we do this, the better approximation that we'll get. So if we continue to increase the amount of darts that we use, we'll get closer and closer to approximating this target density that we have. Okay, so that was kind of just like a normal distribution. But we can use this to sample from like any arbitrarily shaped weird density that we want. So let's say that maybe we had a density that looked like this. We can do the same thing where we throw all of the darts at the board. We separate out the ones that lie above and below it. We reject the ones that are above it, drop everything down. And these are actually now distributed according to this particular distribution. And so we can do the same thing here where we bin everything up. And then, there it is. Okay, pretty cool. Okay, that was kind of an intuitive explanation for what's going on there. You can kind of visually see what's happening. But ultimately, we want to like specify all of this in math so that we can use this algorithm a little bit more generally than what we just did. So I'm going to kind of slowly introduce some mathematical notation to what we just did. So let's go back to kind of this normal looking distribution because it's a little bit easier to just see and understand. And we're going to just first assign some kind of like dimensions to our dartboard. So we're going to say that this axis of the dartboard is the variable tau. So this is the trajectories. These are like the samples that we actually want to draw. And we'll say, for example, maybe it goes between -3 and 3. And then this dimension of the dartboard is kind of the height. So it's like the height of the sample on the board. So we're going to call it h. And maybe it goes between 0 and 0.6. Okay, so now let's kind of write out the steps that we just took in order to actually draw samples from this distribution. So the first thing that we did was we threw darts uniformly at the board. And so you can imagine, if you're actually doing this with a dartboard, you would like throw a dart and then like, I don't know if some really talented person could actually like uniformly throw darts at a board. But we're gonna actually break this up into a two-step process. So it's gonna kind of mimic the same thing that would happen if you were able to uniformly throw darts at a board. And this might seem kind of weird or silly at first, but the reason is because we're trying to like work towards this general algorithm that we can kind of write down mathematically. So that's why we're gonna kind of break it up into a process that might seem a little strange. But basically the first thing that we did, or the first thing that we might do, is sample from a value along this axis of the dartboard. So we'll sample a value uniformly between -3 and 3. And then once we pick a value here, we need to pick a height uniformly on the dartboard. So then we just sample a value uniformly between 0 and 0.6 to get the height of the dart. And if we repeat this process for a bunch of darts, so maybe for the second dart we do the same thing, where we sample a value between -3 and 3, and then we again sample a height between 0 and 0.6. This is actually an equivalent process to just throwing darts uniformly at the board. So we've just kind of broken it up into two steps to kind of obtain the position for every single dart. So then we repeat that a whole bunch of times, and we get our darts uniformly distributed throughout the board. And then we rejected any darts that lie above the blue density. And then we moved all the remaining darts to the bottom of the board. Okay, let's go one more time through that process and add a little bit more math. So now what we're going to do is we're actually going to give a name to kind of this blue density that we were trying to sample from. And we're going to call it P bar of tau. So you can imagine, or as I kind of mentioned, when we talk about unnormalized densities, we typically use this bar. So that's just the unnormalized density we want to sample from. And then the first thing that we want to do is sample a value uniformly between -3 and 3, so along this axis of the board. And to do that, we're just going to specify the actual distribution that we're sampling from here. So we're going to say that tau comes from some distribution that we call Q of tau. And in this case, if we're sampling uniformly along the bottom of the board, that Q of tau is a uniform distribution between -3 and 3. But this is the exact same process that we were doing before. So now we're just kind of defining the distribution that this actually comes from and drawing a sample from this distribution. Okay, and then the next thing that we did was sample a value uniformly between the bottom of the board and the height of the board. And the way we're going to write down this process might look a little bit strange at first, but all that's going on here is we're saying that we're going to sample H, or H is going to be equal to some value C times Q of tau, and C is just a constant that we pick. So we're going to pick C such that it brings Q of tau up to the height of the board. So C times Q of tau gives us kind of the height of the dartboard. And then we're going to multiply it by this value that we call R, which is just some sample from a uniform distribution between 0 and 1. So we're taking the height of the dartboard, we're multiplying it by some number between 0 and 1, and that's going to give us the Y position, or the H position of our dart. So it's still the same exact process, we've just added in kind of some more variables to describe what's going on. Yeah?
If we specify Q of tau, does that mean that this H then depends on tau? Which tau we first sample?
Yes, yeah. So the question was, does H depend on tau? I mean, for this Q of tau, no, because Q of tau is uniform. In a second, we're going to talk about how maybe we don't want to use a uniform distribution for Q of tau, and then H is actually going to be sampled from like let's say the distribution was like this or something. H would be sampled from the point on the distribution and the bottom. So it's like you get a sample from that distribution, and then you like sample uniformly up to its height. Does that make sense? Yep.
This procedure makes sense, but can you go over more carefully why we can't just sample the two axes as independent? We independently sample two values, x and y, or tau and h.
Why we can't do that?
Yeah.
That kind of is what we're doing. So the first time we're sampling tau, and then kind of regardless of tau, or now we're like looking at that tau. Oh, you're saying like why does this depend on tau?
Yeah.
Oh, I think it'll become more clear in a second. Yeah, so I mean for now it really doesn't, because like the Q of tau is, the height of the board is the same at every tau. But imagine that the height of the board was not the same at every tau. Maybe the board was like shaped like this or something, which we're gonna see in a second. Then like we wanna sample between the bottom and the height of the board, and that height would change depending on where tau is. I think it'll be visualized in a second. I think it'll make more sense. Okay. So then the next thing that we do, so we now have like sampled all of our darts using this process. And then we're gonna reject any darts that lie above the blue density. And mathematically what that means is we just look at this value that we got for the height, and we check if it's higher than our unnormalized target density that we're trying to sample from. And if it is, we'll reject it. And then finally, we move all the remaining darts to the bottom of the board. And in order to do that, we just want basically this, the value on this axis. We don't care about their height anymore. So all we do is just kind of keep around the tau value of all of the samples. And that's how we get our final samples. So now we're just gonna have a bunch of samples of tau, which is what we were trying to get, which are the samples from the target distribution. And then there's one more thing I kind of want to note here. So if you kind of look at what's going on here, we rejected all of these gray samples, and then the samples that we ended up with from our target distribution was just all of these blue ones. So if we wanted, for example, say 100 samples from our target distribution, we have to throw more than 100 darts because we're going to reject some of them. And so we want as many samples as possible from our target distribution in the end to have kind of a better representation of that distribution. And so you can kind of think of all these gray darts as like wasted samples. So these are things that didn't in the end contribute to a sample in our target distribution. And so you could imagine that, you know, this might be inefficient if we waste quite a few samples. And what if instead we could sample from a dartboard that looked like this, for example? So now we waste kind of way fewer samples. There's way fewer samples that got rejected. But we need to then make sure we're able to actually sample darts from this dartboard, right? And so kind of what the point is here is like, we can do this, and in fact, we should try to do this. We might not always want to use like a uniform distribution, like that perfectly rectangular dartboard like we were using before. But we just need to select Q of tau, then to be a distribution we can sample from. So we need to be able to sample from this purple distribution. And then we need to select a C, a value C, such that that distribution is always higher than our target. Because you can imagine if it's, you know, lower than our target, then we're going to miss out on some of that region we need. Yeah. Great question. So the question was, why don't we just make it exactly p bar tau? Does anyone have an idea for why? Yeah.
guessing we don't actually have p-bar tau?
Yeah, exactly. So yeah, here it looks a little silly because these both look like normal distributions and we can sample from normal distributions. But you can imagine p-bar tau is like some crazy distribution that we want to sample from. We need to then be able to draw the samples from it. And the whole point of this process is that we don't know how to draw samples from it. And so we need to sample from a distribution that we do know how to draw samples from in order to produce samples from this distribution.
Things like how much information do you have about P of tau that we can guesstimate like how close?
Yeah, that's a great question. So the question is kind of like, how do you pick C? Like, how do you know that, it's going to be always above? So in this case, where it was one-dimensional, we could actually just like plot it and see and understand. In general, you do need some domain knowledge to be able to pick a distribution that fits those requirements. And furthermore, this is actually one of the biggest challenges and kind of drawbacks of rejection sampling is that like sometimes it's not easy to pick that. And there's actually an example in the book that I'll point you guys to later where we show that like if you're trying to do this for the pendulum, for example, you might get something that's like so large that you have to scale your distribution by that it's just not even useful anymore. So yeah, it's a great question. Yeah.
I think I have like a gap conceptually. Why like we don't know the blue distribution, so we can't directly sample from it, but we can like do step 2 where we reject all samples that are greater than the blue distribution. Like how do we know the blue distribution in that step but not in the first step? Yeah, okay, good question. So the question is like we don't know the blue distribution, so like we can't sample from it, but then like how do we go about computing this? So the answer is we only need to know the unnormalized density. So we do have to know the unnormalized density for the sample for the distribution that we're sampling from. If you remember, that gives us the entire shape of the distribution, just the unnormalized density. So what we don't know what the true density is with like, because we don't know the normalizing constant, as long as our like purple distribution, so the height of the dartboard is above our unnormalized density, all of this will still work. Okay.
Yeah.
Notation question in general. Why is it that we're not saying it's h larger than p bar tau?
Well, if you remember, h can depend on tau. Like in this case, the height of the board actually depends on tau, right? The height at this tau is different from the height at this tau.
But like, oh, so then it's like h of tau, I guess.
You could say h of tau if you wanted to.
Okay.
Yeah. And then h of tau would just be equal to like some constant times the q of
And
tau.
also, sorry, further into the question. We have tau is drawn from q tau, but one tau is the actual tau and the other one's a t, or am I just blind?
Here.
Yeah, like here.
And here?
Yeah.
These are the same tau.
But what you get out of the distribution is not what you put in as a parameter distribution.
So we're saying the density of that distribution is, this might actually be I might need to like have a tau in here or something to like show.
I think the confusion is on you have like tau sim q of tau, right?
Yeah.
It's the of tau in the parentheses.
Oh, yes. Actually, that's a notation error. We should have just like a dot in there.
Okay, got it.
Yeah, good point. I'll fix that. Yep.
I think going back a little bit to Ali's question, like, how do we know if it's on that distribution?
So given a tau, so the question is like, how do we know if it's in this distribution? So given a value for tau, we know how to compute p bar of tau. So that was like computing the numerator of that equation that we were talking about. So we can compute p bar of tau. We also know how to compute, like we know what q of tau is, we know c and r, so we can also compute this side and we just do that check. Other questions? Yeah.
But sorry, can you repeat how you spell p-bar? Is that just hard to say?
So p-bar is like the target density that we're trying to sample from. So in a second, I'm going to kind of tie this all back to the failure distribution. So in this case, like the target density we're interested in this class is the failure distribution. So it's that like indicator function times p of tau that I was talking about earlier.
But to develop that, we need to have samples, like failure samples, right? Like to get an understanding of the p-bar.
No, you just have to know, so if you remember that numerator was just that indicator function times the nominal trajectory distribution. So given a value for tau, you need to be able to check whether or not it's a failure, and you need to be able to compute the nominal likelihood, but you don't need to like have any samples of failures ahead of time. Yep.
In 1B, you say sample the value uniformly between 0 and 0.6. And this value is something, it's R, right? Which is then actually sampled from 0 to 1. Is the 0.6 just a random from the example?
Yeah, I mean it's random from the example, but like I'm saying that's in the example C times Q of tau, not for this anymore, this is different, but C times Q of tau is 0.6. Because the height of the board was 0.6. That was just arbitrary. But in general, like you're sampling a value uniformly between 0 and C times Q of tau. That's like what this step ends up doing.
Oh, okay, but then you say R is from 0 to 1. In the same line, R is...
Can I just reply with that? Math isn't my strongest subject, so I'm not going to answer that. R is between 0 and... R is between 0 and 1, but then we're multiplying this value by R.
Okay.
So we're like scaling it by some values between 0 and 1. Yeah. I'm going to try that one. Next time you guys dump me, I'm just going to go math Awesome. Okay. So we're going to actually depart from this dartboard analogy now and talk about kind of more generally what rejection sampling looks like. But before we do that, I just want to give you a random fact about darts. So maybe you already know this, but I didn't know this until I looked this up. So it turns out dartboards are actually designed to specifically reward accuracy and penalize inaccuracy. So for example, like the 20, which is the highest value you can get, is like up here, and it's next to 1 and 5. So like if you're aiming for the 20, then like you'll be in good shape if you're super accurate, but if you're like a little bit inaccurate, you might like really lose out and get 1 instead. And so this is completely outside the scope of the class, but one kind of interesting thing here is you might imagine that if you're actually not that accurate, so like if you're like me and like you're lucky if the dart even like lands on the board, then you probably don't actually want to aim for the 20 because you'll probably miss and get something like much, much worse. And so then you can think about like, okay, well then I don't know what to do. What should my optimal darts strategy be if I'm really not that accurate? Well, no worries, the Stanford stats department has you covered. So there's actually this interesting paper that came out where they kind of assume a Gaussian distribution over like it's centered at where you're aiming, and then there's some variance that says like how bad your aim is, and they can actually get you a personalized heat map of where you should aim to maximize your score in darts. So if you're interested, you can check out this paper. It was also written by Ryan Tibshirani, who's the son of Rob Tibshirani, who actually has 5 times the amount of citations as Einstein, which is pretty cool. Okay, so yeah, you can check that out on your own time if you're interested. But let's get back to rejection sampling. So now I'm just going to rewrite the algorithm one more time, and we're not going to talk about darts or dartboards anymore. So the first thing that we do in the algorithm is we sample some tau from our Q of tau. So you remember that was kind of sampling along the width of the dartboard. And then just kind of a note here, Q of tau is often referred to as something that we call a proposal distribution. So this idea of proposal distribution is going to come up a whole bunch in the next couple weeks as we talk about failure probability estimation. Basically, what a proposal distribution is, it's just a distribution that we're sampling from, that we know how to sample from, in order to end up getting samples from this distribution that we don't know how to sample from. Okay, and then we basically said we reject this dart if C times Q of tau times R is greater than this P bar is greater than our target density. So I'm just going to rewrite that a little bit. I just divide both sides by C times Q of tau. And then just to switch it to like a positive, I'm going to say we'll accept the dart if R, which we sampled between 0 and 1, is less than this particular value here. So this is kind of the criteria we use. And R, if you remember, was just a value that we sampled uniformly between 0 and 1. And so in most programming languages, you can just do that using a call to the rand function. So that's kind of what we do. And then one note here, as we were saying, we needed to make sure that the dartboard was basically tall enough to cover our full density. And so what that's saying is we need to select a proposal distribution, Q of tau, and a value for C. This should probably also note that, such that our target density we're trying to sample from is always less than or equal to c times q of tau. Yeah.
So I think previously in the board analogy, the sort of sampling, the distribution that we sampled tau from was not necessarily the height of the board that we used, like I guess this q of tau, but in this case they're the same. So is that?
So the height of the board in the board analogy is c times q of tau.
I see. So they are the same.
They're the same thing, yeah. Yeah. I mean, another place where this breaks down is like now we can do this over like the full infinite line as well. Like we don't really think about infinitely long dartboards, but now like we don't have to worry about that. We just need to make sure that for all values of tau, this inequality is satisfied. Yeah.
Sorry, can you talk about what the point about band is?
Yeah, so this is just kind of an implementation detail. So maybe I'll just pull up the algorithm real quick. Like, if we want to accept or reject, you remember R was sampled from a uniform distribution between 0 and 1, so we're kind of sampling like where that height should land.
Oh yeah, this makes sense. So this is only true if your proposal distribution is, this is only true if your proposal distribution is uniform, right? Like you can only do this if your proposal distribution
Is what?
uniform.
Uniform. No. So you remember that when I switched the dartboard to be that like funky shape?
Right.
Yeah, so your proposal distribution can be shaped like anything as long as this condition is satisfied.
But rand gives you a uniform.
Yeah, your proposal distribution is q of tau. So the first sample we draw is from the proposal distribution. That gives us our location along the width of the dartboard, if we're thinking of the dartboard analogy. And then the second thing we do is sample that height, and we're sampling kind of uniformly between the bottom of the dartboard and the top of that dartboard at that value for tau.
Oh, okay, got it.
Yeah. Yeah.
I'm a bit surprised that Q can like overbound P. Like I feel like one distribution cannot strictly overbound another distribution.
Yeah, that's what C is for. So you typically need a C that's like greater, or oftentimes you'll need a C that's greater than 1, so you can lift Q up to overbound it. Yeah. Yeah.
Kind of in line with the questions before, I still don't really understand. So if we have the unnormalized distribution, Bailey distribution already, and now we're drawing all these samples and we check them, and then we're approximating kind of this unnormalized distribution again. So I don't really understand what we're gaining by it.
So the question is kind of like, what do we gain from this? So the unnormalized distribution, we just had like an expression for it. So we had like this indicator function times p of tau. But like, you know, for the simple Gaussian, we could like visualize what that looked like. But in general, we can't really like visualize that. Like you can imagine for the grid world, we're just like, it's all the samples that are failure samples weighted by their likelihood in the nominal trajectory distribution. But we don't know what that looks like. So we have the expression for it, but we want to actually draw samples from that expression, or from the distribution that corresponds to that expression. And so this is allowing us to actually like draw the samples. Yeah.
I'm just curious. My intuition is telling me that basically what we're trying to do here is, you can imagine if Q of tau was just uniform, then we're essentially just doing a frequentist empirical sort of estimation of what the failure probability is or distribution is. And then in a more ideal setting, we move our Q of tau, our uniform distribution, closer to, so that we sample more directly like what we think will be failures. And then that will just give a more efficient way to approximate like our failure distribution.
Yeah. I think that's exactly along the lines of thinking. I'm not sure uniform distribution is what you mean, but I'll show you in a second. Like we're basically gonna go through almost that exact thought process. Yeah. Okay, and then just to show you what the algorithm looks like in the book and kind of point these things out. So basically at each step, we sample a trajectory from our proposal distribution Q of tau. And you remember now we're talking specifically about like these trajectory distributions. So to sample, we do a rollout. And then this part here is just we call ran, so that gives us this R, and we check if it's less than this value that we compute here. And if it is, then we accept the sample and we add it to our samples, and if it's not, then we just go to the next iteration. Okay, so that's rejection sampling. So here's it all kind of summed up. We just sample from our proposal, accept it with kind of probability proportional to this, or probability of this. And then we need to make sure that we pick our distribution such that they satisfy this. Okay, and so then what this tells us is that we can actually produce samples, Yeah, so let's talk now back to like we're trying to sample from the failure distribution. This was like our ultimate goal here. And so, okay, I didn't want to show that part yet. So I'm gonna write some stuff out here. So this is kind of our goal here. And so what we need to do to apply rejection sampling in this scenario is we're gonna say our target density, so that P bar of tau here, this part, for our failure distribution is that P bar of tau given that tau is not in the specification. And then we said that this was equal to our indicator function times the nominal trajectory distribution. So that's our unnormalized target density we want to sample from. Now we need to select a Q of tau. We need to select a proposal. So let's kind of imagine here that, let's try out the nominal trajectory distribution. So let's just say that Q of tau is the nominal trajectory distribution. So we know how to draw samples from the nominal trajectory distribution, we just perform a bunch of rollouts. So we're gonna say Q of tau is equal to that P of tau, that's our nominal distribution. And then we need to select a value for C, and this needs to hold. So I'm gonna just plug that in there. We know that P bar of tau is equal to this. So it must be the case then that kind of this indicator function times P of tau is less than or equal to this kind of C times Q of tau. So C times, and we're saying Q of tau is equal to P of tau. So C times P of tau. And so we need to select a value for C such that this inequality holds true. Can anyone tell me a value for C that would work here? 1, yeah, exactly. So if we plug in a 1 here, we just get that, so this becomes 1, 1. So this indicator function times P of tau is always going to be less than or equal to P of tau, because this is either 1 or 0, so it's either going to be equal to P of tau or 0. P of tau and 0 is always less than or equal to P of tau. Okay. And so if we let C equal 1, then kind of our algorithm reduces to this. So the first thing that we do is sample tau from Q of tau, and our Q of tau is a nominal trajectory distribution. So we'll say sample tau from nominal. And then we're going to accept the sample if R is less than this kind of P bar over C times Q, which is going to be equal to this. Whoops. So these two things cancel out, and we just get the indicator function left. Okay, and so this might have all seemed a bit convoluted and weird, but we actually just derived a kind of very obvious result, because this indicator function is equal to 1 if tau is a failure, and 0 otherwise. And so basically the probability that we accept the trajectory is 1 if it's a failure, and 0 if it's not a failure. So all we did was say, sample from the nominal distribution, and if we get a failure, keep it, and if we get a success, throw it out. And we actually talked about this in previous lectures. I showed this as kind of a baseline method to sample from the failure distribution. So all of this seems kind of crazy, but we just derived kind of a very intuitive result, which is just like sample from the nominal distribution and keep the failures. And those failures will actually come from the failure distribution. Okay. So basically what we just showed, oh yeah.
I'm sorry, I'm not quite following the notion of R. Like,
Okay.
It does make sense, but why do we have this other uniform distribution that we're sampling from and checking against?
Okay, another way to kind of look at it is you'll say like, we accept the sample with probability proportional to this value. That's another way to look at it. Or sorry, not even proportional to. We accept the sample with probability of this value. And so to, decide whether or not to accept it, we could just sample between 0 and 1 and see if it's less than that value, and that would allow us to accept with that probability.
Right, I guess the thing that's not super intuitive to me is, why is this now probabilistic if we can check against an unnormalized distribution already? and we know if something is out of that or something is in that. Like a particular tau, we know is either in that or out of it. Why do we need to then make it another probabilistic thing of like we want to accept it with this much probability?
So the kind of intuition is like you want to, if you want to draw samples from a distribution, let's say I just like drew a density function from you and I was like, you give me some samples from it and then you're going to like pretend to draw samples. You're going to give me more samples from areas where this value was higher than you are for areas when this value is lower. So what you want to do is like, let's say now imagine that like I gave you kind of this dartboard where you're doing this. You want to accept more frequently where this is higher and less frequently where this is lower. So it's just kind of a probabilistic way to like meet that criteria.
Let's talk opposite.
Okay, sounds good. Yeah, totally happy to talk offline. Any other questions?
Does this just become direct sampling?
Yeah.
Yeah, I think in this case, it's kind of what I was showing you where, yeah, we just like reject other ones. But what might be a problem with this method? Hint what keeps coming up in this class, yeah.
We probably don't want to be sampling from Q of tau, but something closer to...
Yeah, so exactly what you were talking about earlier. So if we just do this and failures are really rare, then we're not going to get very many failures and we're going to reject a whole bunch of samples and we're not going to be left with very much. So this is kind of an issue. And again, it'll be inefficient for systems with rare failure events. And so one solution is to try to come up with a better proposal distribution that's actually like closer to the distribution that we're trying to sample from. Okay, so let's see a Pluto notebook for this. So let's look here. So this is what we were doing where we make our proposal distribution the nominal distribution. So this is exactly what we're saying. It's kind of just like this direct sampling idea, and we'll just reject the ones that aren't failures. So as we increase the number of samples, you'll see that we get kind of, so this is showing like that dartboard I was showing before, where the dartboard is shaped like this basically. And then this plot down here is showing the true failure distribution, which we can compute for this kind of small toy problem, plotted against a histogram of the samples we're getting. So you can see like as we increase the number of samples and produce more and more samples, we get something that's kind of roughly shaped like that distribution. But as we were saying, this might be really inefficient for rare failure events. So let's make failures more rare by kind of moving this threshold to the left. And so you can see kind of as I move this threshold to the left, now we're at a point where, I'll leave it around here. We're at a point here where like this is starting to break down. Like these don't really look like they're distributed according to this density anymore. And so we might be able to do better if we select a new hand-designed proposal distribution. So here, what I'm going to do is control kind of the mean of this proposal distribution, and then we'll control this value C that tells us kind of how tall that distribution should be. So which way, well, there's already kind of an option because I'm already at 0 here, but which way should I move the mean? Yeah, to the left. Okay, didn't really have an option to move to the right. But yeah, so I'm going to kind of center this mean now around where our failure threshold is, because that looks like it'll get us kind of the most. And that's already starting to improve kind of the results that we get. And then what we can do is, this is kind of super inefficient because this is like way above the failure density. We might as well just try to kind of move this down a little bit. And so if we decrease C, you'll see that we can get, kind of even better results because we're rejecting a lot fewer samples. We're getting a lot more samples to represent our distribution. Can anyone tell me what they think would happen if I decrease C past this?
Yeah, I think probabilities that kind of go above the white part would get not counted, so you would get kind of an underrepresentation at the peaky part.
Yeah, that's exactly right. So the whole process kind of breaks down. So that requirement we had that it'd be greater than, it'd be high enough, is now broken, and so we don't get the right distribution here. So what we want to do is kind of make C as small as we possibly can, but without violating that property that we need. Okay.
But just to be clear one more time, it's generally not easy to tell if the C is like appropriate or not, right? We don't have that. I mean, maybe now it's kind of easy, but in general, it's not easy.
Yeah. So the question was like, is it generally not easy? And yeah, that's absolutely true. I'm going to talk about that actually in a second. And in fact, it's like a lot of times you can pick a value for C by being super, super conservative, but then it will just be like too conservative to be useful. Okay, so what we just saw is that, if we just use the nominal trajectory distribution, this can be inefficient for systems with rare failure events. And then if we try to come up with a better proposal distribution, we can kind of improve this process, but that might be difficult to hand design. So that kind of brings me to what are the challenges or drawbacks of rejection sampling. So one challenge is selecting an appropriate proposal distribution. It's not always obvious how to do this. And then, as we were talking about, selecting an appropriate value for C is also not super easy to do. And if you want to see how this works and like how this breaks down for a bigger example, like the pendulum, example 6.1 in the textbook kind of goes through this process, so you can check it out. Okay, awesome. So let's move on to the next topic, which is also super cool, and that's Markov chain Monte Carlo. So you'll see kind of like some parallels between these methods, like we're going to accept things and reject things. But I think my kind of caution to you is if you try to kind of draw these parallels too much, I think you'll just confuse yourself because they have the same goal to try to sampleize from this unnormalized target density. But we're going to talk about accepting and rejecting, and they're not really doing it in the same way. So I'll just be careful trying to like map these things together. But with that, let's jump into Markov chain Monte Carlo. And again, before I talk about this, I just want to kind of say something about it. So when I first heard of this topic, I was honestly like pretty terrified of it. I feel like it just seems like this kind of scary topic. I don't know what it is. But I want to say that like I think this is very attainable. Like this is a very attainable topic to understand, especially from a practical standpoint. So my goal today is to kind of give you a very practical understanding of this algorithm, how you could use it, what it does, because it's really extremely powerful. With that said, there are kind of these like deep statistical theoretical meanings behind it and proofs behind it. That's kind of beyond the scope of this class, but hopefully this practical standpoint that I'm going to give you is enough for you to like dive into that if that's something that interests you. And if it's not, you could just use this in your work knowing that it works and kind of why and how it works. Okay, and then also with respect to that, I just want to maybe cure some people's imposter syndrome, if you happen to have any, by telling you my first exposure to the word Markov. So I was interviewing for my internship at MIT Lincoln Laboratory, and the group leader had called me and was like telling me about the things I'd be working on and the things that the group there works on. I was interviewing for the group that both Mykel and Robert worked in, which is the group that worked on collision avoidance for aircraft. And they specifically use Markov decision processes for this. And so as the interview was going on, I was like writing down notes of like everything that he was saying so I could remember. And I recently found those notes when I was moving apartments. And unfortunately, I couldn't find them again last night. I really wanted to, so that I could show them to you guys. But I basically reproduced kind of what those notes looked like so you could have an idea here. So it was kind of like something, surveillance systems, collision avoidance, blah, blah, blah. But there was a very funny thing I saw in the notes, which was this. So to be honest, I had never heard of Markov decision processes before that email. So that was my attempt to write Markov. I clearly had no idea what was going on. I later found out that Markov is actually this kind of famous mathematician that lots of things are named after, and it was not, in fact, the words mark off. But just in case, you're feeling a little intimidated or something, like I came this far, so you can do it too. You're already starting off on a better foot because you know what the word Markov is. I'm very glad they didn't see these notes because I'm not sure if they still would have hired me, but it worked out for the best. Okay, so with that, let's dive into Markov chain Monte Carlo. So what we do for Markov chain Monte Carlo is, instead of kind of just drawing these samples one by one, independent of each other, we actually maintain a chain of samples. So the idea of a Markov chain is basically just a chain where the next sample in the chain depends on the previous sample in the chain. And so what we do is we start with some kind of initial sample. We just need to pick something. So we start with some initial sample for tau, and then we build out a chain where the next sample, I haven't told you how, but depends on the previous sample. Then we do that again. And we repeat this process to get kind of this very long chain. And then once we have this chain, we can do a similar thing as before. We just take all of those samples, and it turns out that the samples in this chain, if we kind of drop them all down again, will be distributed according to the distribution that we were trying to sample from. So I haven't told you how any of that works yet, but that's kind of what we're heading towards. So we basically want to figure out how we can make this chain of samples such that when we're done producing them, it will be distributed according to this distribution. Okay, so how do we actually go about creating the chain? So we need to start with some initial sample tau. It does matter a little bit what we start with, but let's not worry about that for now. So we're just going to say we start with some initial trajectory, initial sample. And then at each iteration of the algorithm, we sample a new kind of proposed sample that we'll call tau prime from this conditional distribution that depends on tau. And this distribution is often called a kernel. And to kind of make it concrete, a very common kernel is just like a Gaussian distribution that's centered at the sample that we currently are at in the chain. So it would look something like this. So you have our current sample, and we're going to draw a new sample from a distribution that's centered at our current sample. So for example, maybe we draw this sample, and this is our like tau prime. And then the next thing that we do is kind of a similar idea with rejection sampling, but doesn't quite map exactly the same. But we're going to accept this sample with some probability. And that probability is specifically this probability here, which depends on kind of the nominal target density that we're trying to sample from and this kernel function. And I'm going to give you some intuition for like what's going on here with this probability in a second. But just to get an idea of the algorithm, like we're going to accept with some probability equal to this. Okay, so then we'll call rand or something to decide if we're going to accept it and accept according to that probability. So let's say maybe we are going to accept this sample. So then this becomes our next sample in the chain. And then we just go back to our kernel, which is again this kind of Gaussian distribution that's centered at our current sample. We sample a new kind of proposed sample. And then we decide whether or not to accept it according to this probability here. Maybe this time we don't accept it, so we just keep the current sample that we have. And then we just repeat this process. So maybe we accept that sample, and so on, and we build out kind of this big chain. And the crazy thing is, like, once we're done with that, the samples in that chain are actually distributed according to the target density that we were trying to sample from. Okay, and the cool thing is like this process is actually guaranteed to converge to the target distribution in the limit of infinite samples. So if we sampled forever, we would get exactly the target distribution that we're trying to sample from. Okay, but like what the heck is all of this magic? Like how is any of this working? Why is this even like this? So I'm gonna try to give you some intuition here because it's really not too crazy what's going on. So one thing I'm first going to say is the kernel is often chosen to be symmetric, meaning that g of tau given tau prime is equal to g of tau prime given tau. And so that means that these two things are equal, so we can just kind of cancel them out. So this might seem like a weird, crazy assumption. There's like an exercise that allows you to show that it turns out like the Gaussian kernel I was just showing you is symmetric. So it's not like a weird thing. Like most of the kernels are symmetric, so we can do this. But this allows us to kind of simplify our acceptance probability. So now our acceptance probability is just the probability density of our new sample under the target density that we're trying to sample from divided by the probability density of our current sample. And so just kind of putting all of that aside, again, if I kind of just handed you a density function and I was like, here's what it looks like, and I told you to just like draw some samples from it, more often you would draw samples from the areas of that density that are higher, and then less frequently, but every once in a while still, you would draw samples from parts of that density that are lower. And it turns out this acceptance criteria is kind of, it forces that behavior. So there's kind of two cases here. So the first case is that the target density evaluated at our proposed new sample is greater than the target density evaluated at our current sample. And so in this case, we're saying like tau prime is more likely under the target density than the tau that we're currently at. And that's going to make this fraction here, so this fraction here, greater than or equal to 1. So that means we're going to accept with probability greater than or equal to 1, or in other words, we're always going to accept that sample. So every time we get a new proposed sample that has higher likelihood than the one we're currently at, we're always going to accept it. Now the other case is that the new sample has a lower target density than our current one. So this is kind of achieving the idea of like we sample from a high density more often. And here, If it's lower, we don't necessarily want to keep it because we want to sample from high density more often, but every once in a while we do probably want to put in like a lower density sample in there. And so basically we're saying tau prime is less likely under the target density, so we're going to sample it or accept it with some probability less than 1, and that probability is proportional to how much less likely it is. So if it's a lot less likely, then there's like still some chance that we might accept it, but like a small chance that we're going to accept that sample. And so that kind of gives you some intuition, like what this is hopefully achieving is kind of that we sample from these high density areas more often, but we still sometimes get samples from the lower density areas. This is like in no way a proof that this works, like you'll have to, that's kind of beyond the scope of this class, but hopefully this kind of demystifies what some of the magic that's going on here is, because that's really all that's happening. I'll pause there for questions. Yep.
So based on the value of your old sample, you like create a probability distribution about that, and then you sample based on that to get your new sample.
Yep, yeah, so the question was like, based on the value of your current sample, you create a probability distribution around that. So there's like this thing called a kernel that tells you how you want to do that. So a common one is a Gaussian one where you just create a Gaussian distribution around it and then draw a new sample from that. And then the next step is to decide whether or not you want to accept that new sample and add it to your chain or whether you want to stay at your current sample. And basically we want to accept samples that are like likely according to our target density more often than we accept samples that are unlikely according to our target density.
But the target density is not the probability distribution about the old sample, right? It's like
No, the probability distribution about the old sample is just a way to get us a new proposed sample for our chain. Yep.
I think you're going to talk about this later, but like, could you talk a little bit more about how radiation point affects that answer?
Yeah, I'll save it for later actually, just to save time. But yeah, good question. Okay, so let's, so maybe some of you are still scratching your head, so let's see what this looks like in a Pluto notebook. So let me kind of explain these plots here. Okay, so this first plot here, so we just have one sample in our chain right now, so this is kind of the initial sample that we decided to start with. And so this plot here is just going to kind of show the chain over time the same way we were building up before. And this is showing also our failure region, so we're trying to sample from this region here. The second plot here is going to show the current sample, the proposed sample, so we're using this kind of Gaussian kernel, and our proposed next sample is actually kind of unlikely. We got a sample like all the way out here according to that distribution. And then this is the target density that we're trying to sample from on the same plot. And then this plot down here is going to like show a histogram as we add more samples to it of all the samples that we've seen compared to our target density, so kind of like above what we were doing. Okay, so let's go to the next sample. But before we do that, can anyone tell me whether we're going to accept or reject this new proposed sample? Yep, I see some like down, yeah. We're going to reject it. And the reason for that is the probability density or the target density of our new sample is actually 0. So we're trying to sample from this density here, right? And we're only going to sample, so we'll sample with probability 1 if it's more likely. So it's definitely not more likely, it's 0. And if it's less likely, we're going to sample with the ratio of the new likelihood to the old likelihood. The new likelihood is 0. So we're going to have 0 probability that we accept this sample. So then, if we go to iteration 2 here, you'll see we stayed at the same exact sample. So now there's a chance that we'll accept this sample, and this kind of bar over here is actually showing us like how big that chance is. So this is 0 and 1. So we have a small chance that we'll accept this new sample because it is much less likely than this one according to our target density, but there's still a non-zero chance. So we can go to the next one. Turns out we didn't accept it. Now they're almost on top of each other, so we probably do accept it. And we can just kind of do this for a while and build out kind of this really big chain. And we're not quite looking like the target density just yet after a few samples, but after a while, this chain's actually going to cause the samples to start being distributed according to this target density. So let's just move along a little bit here. So we build out this big chain. Just zoom it out here. So here's our big chain that we created, and it turns out if you plot all of the samples that were in this chain, you get this nice histogram that looks like the target we were trying to sample from. Kind of insane, right? Like just, I don't know, blows our mind. So I think that's all I wanted to show for that part. Yes?
So just in terms of the big picture goal again, like are we trying to find essentially that, like in the very beginning of lecture, that like scaled up distribution of the red curve?
Yeah, so the question is like, are we trying to find that one? So we can't compute that one without computing the normalizing constant, but we're just trying, we can draw samples from it though. So the samples will be distributed as if they came from that distribution, but we can't calculate what the actual like density of that is. Yeah.
Let's say I want to use this in the project, and I want to get really high efficiency in the rejection sampling. Our kind of space of choices was how to design the proposal distribution, and getting a nice proposal distribution gives you efficient sampling. And here, what's our design space? Is it just the like what's kind of a Gaussian? How wide do we want to make it? And if we want to take maybe a non-Gaussian distribution, is this kind of our option?
Yeah, kind of. I'm going to talk about that shortly. Okay. So you can greatly improve this kernel that we're using and do some other things.
You mentioned that the Gaussian kernel is symmetric, and I guess it's useful, but could we also take a non-symmetric kernel?
Yeah, you could take a non-symmetric kernel. It just won't reduce to that. So if you remember, the original acceptance criteria I had was like p tau times g over p times g or whatever. That g won't go away, but you can still have a non-symmetric kernel. Yeah. Okay. Okay, so we saw that, as we increase the number of samples, we get this distribution that we want. Okay, but here's kind of the catch here, which is like this all works, so it seems amazing. It all like converges to the target distribution, but there was kind of this extra thing I said, which is like in the limit of infinite samples, and we don't have time for that. So we don't have time to draw infinite samples, unfortunately. And so, there's a lot of kind of heuristics and things people use in practice, because like no matter what kernel, whatever you use, like it's going to converge to the thing you want in the limit of infinite samples, but we don't really want to try to draw infinite samples, and so we need to do some things to kind of make this work more efficiently or perform better when we don't have that. So again, we kind of deploy these extra tricks in practice to kind of make it perform better. So let me go back to this Pluto notebook to kind of explain what I'm saying. Okay, and so here we're actually going to get back to talking about the initial sample that we start with. So here we started with an initial sample that's in the failure region. Let me zoom this back in again. Let's go back. Let's say now that we start with an initial sample that's like outside of the failure region. So maybe it's got a value of like 1 or something. So now we start with this initial sample. Here's our new proposed sample. They both have 0 likelihood, so we're not going to accept the new one, and we're kind of stuck at this bad initial sample that we picked. And it's going to take us a while. We're not going to accept a new sample until we get something from our proposal that's in this like failure region. And so what's going to kind of happen here is we're going to get this kind of period of time where things aren't really looking so good, and like we have this random extra peak of our distribution out here. In the limit of infinite samples, this will look like 0 samples at all, but right now it doesn't look like that. And so that's not super great. And in general, kind of at the beginning of MCMC, as depending on where we start, this doesn't always, like kind of the first few samples don't always really look like the distribution that we're trying to sample from. And so a common thing people do is they say that there's kind of like this burn-in period. We're just going to throw out the first however many samples. So for example, let's just say we want to throw out like the first 20 samples. So we threw out all the samples in this region. That got rid of that. And now we can just kind of draw the rest of our samples, and everything looks reasonable from there. Okay, I think that's all I wanted to say on that. Yeah.
But we're never going to get stuff that's outside of the failure distribution, right? So if we just kept sampling, wouldn't it even out?
Yep. Yeah. So the question was like, we're never going to get something from outside the failure distribution. Yeah, that's only if we like start in the failure distribution. But in general, like if thinking of just non-failure in general, like depending on where we start, we might not get great performance at the beginning. But yeah. Okay, so one of the things, kind of tricks that we do to make this better when we don't have infinite samples is this burn-in period that I was talking about. Another common thing people do, so one kind of interesting thing is that because it's this Markov chain and the next sample depends on the previous sample, the samples are actually correlated with one another. And so a common thing people do is like this thing called thinning, where they'll just kind of keep every, for example, 5th sample, every 10th sample, whatever, to kind of get rid of that correlation as best they can. And then finally, there's this thing called smoothing. So let me go back to the Pluto notebook and explain this again and show you kind of what the problem is here. So let's now imagine that we have multiple failure modes. So now we're saying that our distribution or our sample is going to be a failure if we sample something that's too low, and also if we sample something that's too high. So we have these two kind of distinct failure modes, and then 0 likelihood for our failure distribution in the middle. And then let's see now like what happens if we try to apply MCMC to this. Okay, so can anyone guess kind of, so what went wrong is we only ever got samples from this failure mode. Can anyone kind of guess why this happened or what might be going on here?
Well, assuming that the G distribution is perturbing only a small amount, it's really hard to perturb your way all the way to the right.
Yep, that's exactly right. So you're saying, this only perturbs it a small amount. So how are we going to perturb ourselves like all the way over to this failure mode? And even if you just look at this example at the end right here, here's our current sample. Here's the distribution over possible next samples that we're going to get. There's a very low likelihood that our next sample is going to be all the way over here. So that's kind of the issue. We're not really, eventually, in the limit of infinite samples, this would eventually actually happen, and we would jump over to this failure mode, and then maybe we would jump back, as we sample for infinity. But since we, again, don't have time to do that, we need to kind of come up with a better way. So that kind of motivates this thing called smoothing. Okay, and the idea here is that we kind of need to help the algorithm move in between these failure modes, because it's very unlikely that it'll just kind of do it on its own. And we can do this by kind of smoothing out the failure distribution. So these kind of 0 positions here, we maybe want to make them slightly non-zero. And so the way we do this is we define this distance function that we'll call delta of tau. And this distance function is just a function that's 0 if tau is a failure. So it's kind of like distance to failure if you are a failure is 0. And then it's greater than 0 otherwise, and it should get closer to 0 as you get closer to a failure. One really easy way to do that is to just take the max of our robustness function with 0. So if it's a success, our robustness will get lower and lower as it gets closer to failure. And if it's a failure, robustness will be negative, so we'll just return 0. In that case. So that's one really easy way to kind of get this distance function. And so then we can kind of rewrite this unnormalized density here. So before we had this indicator function that says, it evaluates to 1 if tau is if tau is not in the specification, if tau is a failure. And we can say now we know if it's a failure, then that means that this distance evaluates to 0. So we can just replace that condition with this distance being equal to 0. Okay. And so now we can think about this. That's not supposed to have a p of tau there. Hold on, let me just. Okay, that's not supposed to be there. This indicator function is actually kind of similar to a normal distribution with kind of a tiny variance. So you can think about it like this. So when delta tau is 0, the indicator function returns 1, otherwise it always returns 0. We can say that's kind of similar to this distribution that's centered at 0 with some kind of tiny variance, but not quite the same, right? Because now we're assigning non-zero values to values that are not 0. So then what we could do to kind of smooth things out is we could just take this indicator function and replace it with this like normal distribution with this kind of tiny variance. And so now this smooth distribution will assign non-zero probability to successes with higher probabilities for successes that are closer to failure. So I'll kind of show visually what this looks like in a second to get kind of more intuition here. But one more thing to note is like this parameter epsilon kind of allows us to control how smooth that distribution, how much smoothing we're applying. So if it's 0, we're back to our indicator function, we have no smoothing. As it approaches affinity, you can imagine like a normal distribution with infinite variance, kind of almost just looks like a uniform distribution at that point. It's like super wide. And so this almost just turns into a uniform distribution, and this just turns into p of tau. So it actually approaches the nominal trajectory distribution when it's equal to infinity. Okay. I'm just gonna go through this really fast, and I'll go through it again at the beginning of lecture because I just want you guys to see it before this lecture ends in 2 minutes. Okay, so when we now have a bunch of samples that are not failures, yes, but we can just reject them and we'll be left with samples from the failure distribution. And you can actually think of this as just doing rejection sampling with our smooth distribution as the proposal distribution, which is pretty cool. And let me just show you this cool animation to incentivize you to come back after the weekend, and I'll explain how it actually works. So here's with like a small amount of smoothing, we still don't get this extra failure mode. You can see kind of this smooth distribution. If we increase the amount of smoothing, let's go like here. If we increase the amount of smoothing, you'll see it actually starts to kind of jump back and forth between failure modes, and this is kind of that smooth failure distribution we end up with. And then we get a nice set of samples from both failure modes. All right, yeah, we'll talk more about that on Tuesday.